We'll go ahead and jump into today's material. Now, the starting material for today, I introduced much earlier than the author introduces it, which is sets. If you think all the way back, first we did propositional logic, then we introduced predicate logic, then we introduced set theory. And I've been trying to get you all throughout geometry to think about geometric objects as sets of points. Right? I've been trying to get you to think about lines as sets of points and all these figures that we make as sets of points. Now, the author is formally trying to get you to think about the same way. I like to get you thinking about it all the way at the beginning of the class. So we're going to be recapping some of the stuff that we already covered forever ago, clear back in lecture 3. And so we're going to cover it somewhat quickly. So, first off, so the next chapter is on loci and sets. We'll get to what exactly loci are. But starting out with sets. Intuitively, what is a set? It is an unordered, unique collection. What do we mean by that? By unordered, we mean that the order inside of a set does not matter. And by unique, we mean that duplicates do not matter. So to signify a set, we do our curly braces, our curly bracket here. We comma separate the elements of the set, and then we do a curly bracket to end the set. So this is a set containing the elements A and B. This is also the set containing the elements A and B. These two sets are equal to each other. The fact that the order is different is completely irrelevant. And then finally, it's also equal to a set containing A, B, B, A. Because duplicates don't matter. Question, how many things are in the set? Just 2 things, A and B. There are not 4 things in that set, there are 2 things in that set. Sets. Okay, we have this notation. X is in A. We've been using this notation throughout class, but what does that mean? That means X is a member of set A. Anytime you see this, you can instantly infer that A must be a set. That's the only time we use that notation is relative to sets. So as an example, 1 is in the set containing 1 and 2. 1 is not in the in symbol with a line through it. 1 is not in the set containing 2 and 3. The set containing 1 is not in the set 1, 2. This is not one of the elements listed out in here. The elements listed out in here are 1 and 2, not the set containing 1. That's nowhere listed out in there. If I were to come and add on to this and the set containing 1, you could stick sets and sets, that's perfectly valid. Now, the set containing 1 is in here. Question, how many elements are in this set? 3, but there's a 1 here and a 1 here. I thought duplicates don't matter. Oh yeah, that's the set containing 1, which is very different from 1. Those are 2 very different objects. Okay, so there we go. Quick recap of basic sets and the in notation. Next we have a subset. What does it mean for A to be a subset of B? That means if X is in A, then X is in B. Everything that's in A is also in B. If you can find something in A, it's also in B. That's what it means for A to be a subset of B. The set containing 1 is a subset of the set containing 1 and 2. Everything you can find in here is in here. If something's in here, then it's also in here. Make sense? The set containing 2 and 3 is not a subset of the set containing 2. Everything that's in here is not in there. I can find something over here that does not show up over here. Pick any set A, always and forever, A is a subset of itself. Is everything in A also in A? Yes. So every set is a subset of itself. Now, we have the notion of set equality. Do I dare say this? Sorry, think about something for the logic people. I'll say it, and just don't get confused. Teacher's advice, don't get confused. Very useful. All right. So here I'm saying what it means for A to equal B. Wait a second, isn't equals a concept of logic? Yeah. Isn't logic and the law of identity what dictates what equals means? How can I decide I'm going to define what equals means here? And the answer is we are extending the notion of equality. So equal still means what it means in logic. So I know for logic that the set containing 1 and 2 is equal to the set containing 1 and 2. Logic tells me that because I have identical symbols on both sides. Everything is identical with itself. But it does not tell me that the set containing 2 is, the set containing 1 and 2 is equal to the set containing 2 and 1, which is what I want to be the case intuitively. And so we are extending the notion of equality in set theory. So it still means everything in logic, and we're extending it. So extending the definition of equality, what does it mean for set A to equal set B?
A is a subset of B.
Yeah, it means A is a subset of B and B is a subset of A. If everything that's in A is in B and everything that's in B is in A, then they're equal, which is what we have right here. Pick anything you want out of this set, it's also in this set. Pick anything you want out of this set, it's also in this set. Therefore, the sets are equal.
Is that a definition, or can you prove that as a theorem?
No, that has to be a definition.
Really?
You cannot get from logic alone that these two things are equal to each other.
Well, with the stuff we have before, it being I don't know.
This is just intuition. Strictly speaking, sets are undefined.
They're undefined?
Yes. When you start set theory, your two primitives are set and the in symbol. Those are your two primitives, and everything else is defined in terms of those.
I see.
So, yeah, these are just intuition. Notice I said, what does it mean for x to be A? It means x is a member of set A. I mean, when you think about it, that's a circular definition.
Yeah.
What does it mean for x to be a member of set A? No, it means that x is in A. That's what it means. So if you think about it, these aren't really defining anything for you. They're just giving you the feel goods.
Okay.
And then from here on out, we're actually defining things. But we're not going to think that heavily about set theory. We'll think that heavily about set theory tonight. Okay, so there's your feel goods. Now, what does it mean for A to be a proper subset of B? That means A is a subset of B and A is not equal to B. It means in some sense A actually has less elements than B. Why do I say less? Well, because they can both be infinite. The naturals are a proper subset of the integers, even though they both have cardinality infinity. So proper subset means it's a subset, but they're not the same. This one, subset, is often thought about like less than or equals. A is a subset of B means it's either a proper subset of B or they're equal to each other. And this one's often thought about like less than. A is a subset of B, A is in some sense less than B. It's missing something that B has, for sure. There's for sure something in B that I can't find in A. So up here, the set containing 1 is a proper subset of the set containing 1 and 2. Over here, A is never a proper subset of itself, because they're always equal. So, not a proper subset of itself. This is a proper subset of that because I can find something in here that doesn't show up in here. Everything in here is in here, but there's something in here that's not in here. That's why A can never be a proper subset of itself. I can never find something that shows up in here that doesn't show up in here. Okay, proper subset. Now, set builder notation. When I'm trying to tell you what some set means. One of the ways I can do it is the way we were doing up here, where I just list out all the items in a set. What happens when you have infinite items? Your arm gets tired. So we don't like that. So we come up with set builder notation, a way of representing very large sets with some sort of notations, like you don't have to write out all the elements. How does this work? You do a dummy variable, typically x, colon, and then you have some condition that x satisfies. All the x's that satisfy the condition are what the set builder notation represents. Let me give you an example. We can say, what are the evens? The evens, those are the set of all x, such that, we read the colon as such that, x is in the integers, so x is an integer, and 2 divides x, or x is divisible by 2. You haven't seen that symbol before, that's fine, doesn't matter, but that just means 2 goes into x evenly. So if x is an integer and 2 goes into it evenly, then it's an even. And this is a way we can write out the evens rather than me writing out the number 0, 2, 4, 6, 8, plus all my negatives I missed.
Yeah.
Okay, give you another example. Perfect squares, the set of all y, where y is equal to x squared and x is a natural number. What's that set? Pick x, any natural number, 0, square it, that gives you your y. What's 0 squared? 0. Pick 1, what's 1 squared? 1. What's 2 squared? 4. What's 3 squared? 9, 16, 25, and it goes on. I can't write them all out, so here's the way we could represent that set. Make sense?
Yeah.
Set builder notation. Again, you already saw this clear back in our third lecture. So, if we're going too fast, you can go back and rewatch that lecture. All right, A intersects B. This is now a set operation. What do operations do?
They return another set.
Yeah. So up here was a set relation. A is a subset of B. That's something that's either true or false. Right? When I say right here, the set containing 1 is a subset of the set containing 1 too. When you look at this whole thing, you call this whole thing true. So that is a set relation. Relations take two sets and spit out true or false. Set operations now are going to take two sets and spit out another set. So our first one that we're going to talk about is A intersect B. What happens when you intersect two sets together? This is kind of like multiplying a number. When I take two numbers and I multiply them together, I get another number. This is going to take two sets, intersect them together, and it's going to spit out another set. So by definition, A intersect B is the set of all x, where x is in A and x is in B. Set of everything that shows up in both those sets. And set union, A union B. What does that mean? So the U that way means union, that one means intersection. A union B, that's a set of all x, where x shows up in A or x shows up in B. So if it shows up in one of them, it shows up in the union. If it shows up in both of them, it shows up in the intersection. Just quick simple example. Let's say A is equal to set 1, 2, 3, and B is equal to set 3, 4, 5. What is A intersect B equal to? What's A intersect B equal to? The set containing 3. It's the set of everything that shows up in both of those. Right? What if B looked like this? Now what's A intersect B? It's a set containing everything that shows up in both.
Yep.
Right? Okay. And over here, what's A union B?
The set containing 1, 2, 3, 4, 5.
The set containing 1, 2, 3, 4, and 5. If it shows up in either set, it shows up in the union. Right? Alright, just quick examples.
Are we, I guess we're not going over to Morgan's laws?
No, we're just briefly touching on it again. This is already as much as the author bothered going into set theory.
Really?
We've already covered what he covers set theory-wise. Just introducing you to the notion of the set, these two operations. We even did a little bit more full than what he does.
Okay.
Because now we're going to talk about a locus. What is a locus? A locus is a set of points satisfying some condition. So it's just a set. It's a fancy word for set, almost. If I give you some equation, like ax plus by equals c, what do you instantly know?
That it's a line. It's linear.
Well, you get that's a line. What is a here?
Some random.
It's a constant, right?
Yeah.
What's x?
It's a variable.
It's a variable. You instantly know right out the door that the x and the y here are variables, and the a, b, and c's are constants.
Yeah.
If we introduce some person who didn't get the same education background that you do, they say, how do you just know that? They're just letters. Right?
Yeah.
And it's just a convention that we adopt, that we use x and y's to talk about variables, a, b, and c's to talk about constants. So when you see locus come up, it's a word that you don't see in earlier math textbooks, but more advanced textbooks use the word more often. It's still just a set, but it's a set where the objects in there are points. So you know what? It's referring to some geometric-like figure. It's a set of points.
Points is undefined here. Right?
Yeah. But the point is, when you see locus, you're instantly thinking geometric figure. Because for those of you used to thinking about a function, for example, as a set of ordered pairs, we don't really think about that as the points that the function represents. But if I wanted to think about it as a geometric figure, I was actually plotting that graph, I might choose to use the word locus now to get you to focus on that aspect of it.
Okay.
So it's just a different word. We never need to use the word locus. We could always say a set of points, and that's perfectly fine. It's just in more advanced books, it instantly lets you know that we're talking about some geometric type figure. So it's not introducing any new concept, it's just a set of points satisfying some condition, the condition that results in the geometric figure you're talking about. That's it. So let's get comfortable with this. You're reading a book, and it says we're talking about the locus of points, a distance r from the point O. So I've got the point O here, and now I want to talk about a set of points, the locus of points, a distance r from O. Let's pretend that r is this distance. Here's my r, the distance from here to here. What are all the points, a distance that from O? Well, let's see, let's measure that. Here's one, found one. Here's one, found one. Here's one, found one. What are all the points this distance from O?
It's the circle.
The circle centered at O, with this as its radius, right? So this is another way of talking about that circle. Okay? Locus, set of points satisfying some condition. And it's going to result in some geometric figure. Okay, let's look at another one. Let's look at the locus of points, distance D from line L. What does that give you?
Parallel lines.
Let's say that this is L. D is the length of that segment. There's D. What are all the points this distance from L?
It's a parallel line from
Should be.
like above and below.
Yeah, it's going to result in a line up here. Call that L prime. All these points on this line are this distance from this line. And another line down here. Call it L double prime. That's the figure being referred to. Good? One more. Let's talk about the locus of points equidistant from two parallel lines.
It's the line L in that picture.
Yeah. Let's say that our two parallel lines that we started with are L and L prime. The set of points equidistant for both of them is a line parallel to them right smack in the middle. Make sense? So, locus of points. Just fancy terminology. Let's just talk about sets satisfying a condition. And then what's loci? It's the plural of locus. Go ahead.
Could you tell us like another scenario of that would like result in a different geometric figure than a circle? Like with the locus, like is there a set that?
I just gave you 3 examples. One resulted in a circle, one resulted in 2 parallel lines, one resulted in 1 line.
Yeah. But I'm just saying, could you do like another shape?
Oh, you'd have to somehow describe the shape as conforming to some condition. So I'm not saying that it's easy to describe every geometric figure as a set of points satisfying some condition.
Can you?
I'm sure you can. It'd be somewhat tedious. But there's often times where the geometric figure we're interested in is a set of points satisfying some condition.
Okay.
So we'll be doing some examples working with geometric figures satisfying some condition. Okay, yeah, I see what you're saying. Any other questions?
When we were talking about loci, is that a set containing sets, or is that just?
No, it's just the plural. Just like you have a set or sets, you have a locus or loci. So, just plural of it. Nothing fancy. Good? Alright, let's hopefully I can get all 3. Yes, I can. Okay. So now, before we start proving our theorems for the day, I need to remind you of the last theorem we proved from chapter 12. So thinking back to chapter 12, what we proved is that the measure of an inscribed angle is half that of a central angle, as long as they're subtending the same arc. What does that mumbo jumbo mean? So, start out with a circle. An inscribed angle is like this angle. That has its vertex on the edge of a circle. And let's say that the measure of this angle is theta, something like 30 degrees. Then if I create a central angle, so this is a point O right here, That's the point O. If I create a central angle, which subtends the same arc, then its angle measure is double that of the inscribed angle. If that's 30 degrees, that's 60 degrees. In other words. You remember that? That was our big ending theorem from last time. Okay, so we'll be using that a couple times. So now jumping into our first theorem of chapter 13. What is the proof here? We are going to prove that the locus of points equal distance from A and B, where A and B are points, are the perpendicular bisector of AB. Make sense? Quick scribble here. If I have A and B, what are all the points that are equal distance from A and B?
That line that goes to the middle.
They're midpoint, obviously, right?
Yeah.
But think about a point right here. That point, its distance from A is the same as its distance from B.
Wait, I hope we already proved this.
And the point down here, its distance from A is the same as its distance from B.
We did already prove this, didn't we?
Like, we proved this before. At least as a homework problem we have.
You may have already come across this. Now we're going to prove it. Think about it in terms of locus of points. Because we're going to introduce you to a proof style here. The proof style relies upon the fact that to show that two sets are equal means to show that they're subsets of each other. So I'm going to come up with a set representing the points equal distance from A and B. And I'm going to pick a set which represents the perpendicular bisector of A and B. And I'm going to show that those two sets are in fact equal. How do I show that two sets are equal? I show that the first set is a subset of the second set, and the second set is a subset of the first set. If I can show that two sets are subsets of each other, then they're equal. So what am I going to do? I'm going to let S1 be the locus of points interior to angle O. So my picture's over here. Oh, no, we jumped. So like, we're not bisecting an angle, we're bisecting a segment. So my picture's over here. So the locus of points equal distance from A and B are the perpendicular bisector of AB. Okay, so let AB be given, and let O be its midpoint. So starting out with this picture, we start out with AB, there it is, O is its midpoint.
Yeah.
Let S1 be the locus of points equal distance from A and B. So S1 are the points equidistant from A and B. And let S2 be the perpendicular bisector of AB. So over here, drawing the same picture again, but this time we're drawing S2. So S2 is the perpendicular bisector of A and B. S1 are the set of all points such that, maybe color this in. S1 are the set of all points such that that is the same length as that. So in S1, if you take a point out of S1, I know its distance from A and B are the same. S2, if you pick a point in S2, I know it's on the perpendicular bisector of A and B. So I know that this is the same distance as this, and this line is perpendicular to it. Good so far? So let S1 be the locus of points equidistant from A and B, and let S2 be the perpendicular bisector of segment AB. Now, here's what we're going to do. I'm going to show that S1 is a subset of S2, and S2 is a subset of S1. How do I show one set is a subset of the other set?
You show that every element, if an element is in one set, it implies that it's in the other one.
Yes. What does it mean for set A to be a subset of set B? It means everything that's in A is also in B. So I need to show everything that's in here is also in here. So I need to show you how you can pick any point P in here you want, and show that means that that point P is also in here. That's what it means for it to be a subset. So start out, let P be any point in S1. Doesn't matter which one. Pick any one you want. I'm going to show you how it's also in S2. So that S1 is a subset of S2. So let P be some point in S1. And note that if P is equal to the point O, then P is obviously in S2. If we happen to pick the point O, O is obviously on the perpendicular bisector.
Right.
So we've already handled the case where you pick O, but now let's handle the case where you pick P and P isn't O. So now, if P is not the point O, then notice that angle PAO is congruent to angle PBO. How do I know that?
Isosceles triangle.
It's an isosceles triangle,
Yep.
right?
These angles.
If P is a point in S1, what does that instantly mean?
It means that it's equidistant.
It means its distance from A is the same as its distance from B.
Well, okay, I see it.
And so, this is a isosceles triangle. And so I instantly know then that this angle is congruent to this angle. What am I trying to show?
You're trying to.
I'm trying to show that P lies on the perpendicular bisector.
Yeah.
So ultimately what I'm trying to show is that this segment is congruent to this segment, and this angle is a right angle. The line from O to P is a perpendicular line, and it bisects A and B.
Okay.
Right?
Yep.
Now I already know, by choice, O is the midpoint. That's why I chose O to be. So I already know that this is the same as this.
So now we just have to show that those are right angles.
So I just need to show that that's a right angle.
Okay.
Continue the argument. Look at this picture.
Those two triangles are congruent.
This triangle is congruent to this triangle. How do we know that?
Side angle side.
Side, angle, side. They have two sides the same, an angle the same, and a side the same. Therefore, this triangle is congruent to this triangle,
So that
which means that this angle is congruent to this angle.
congruent to the
That's a
supplement.
right angle.
And an angle that's congruent to its supplement is a right angle.
Yep. I see it.
You see it? So, just that exact thought process finished out right here. If P is not the same as O, then angle PAO is congruent to angle PBO. Those are the base angles. PAO, PBO. So those two angles are congruent. And so, triangle PAO is congruent to triangle PBO by side angle side. Exactly what you guys already said. So then angle AOP, that right angle, AOP, is congruent to angle BOP, since the triangles are congruent. And so those are right angles, since they're congruent to each other and they're supplementary of each other. So therefore, P is in S2. So pick a random point out of S1, and I showed it also lies on the perpendicular bisector, so it's also in S2. So we just barely showed, we started out with let P in S1, and we showed dot dot dot, therefore P's in S2. Let P in S1, that implied P was in S2. Look at this definition. What does it mean for A to be a subset of B? It means that if X is in A, that implies X is in B. If P is in S1, then P is in S2. See exactly what it means for S1 to be a subset of S2. Now, I'm focusing on the set thing because this is such a common pattern of proof beyond just geometry. When you're dealing with two sets. Sets are ubiquitous in mathematics. They're everywhere. Can't get away from them. So this proof style comes up a lot. The focus here is more on the proof style than what we're actually proving. Getting used to showing that two sets are equal to each other. To show that they're equal to each other, you show that they're subsets of each other. How do you show they're subsets of each other? You pick a random point out of one, show what's in the other, and then pick a random point out of the other, show what's in the one. Very common proof style. In the same way that anytime we see an implication, I say, how do we prove an implication? Assume the antecedent. And you all scream it at the same time so loud, the camera can't even hear it. Right?
Yeah.
Okay, so now we're going the other way.
You're at 7.
Thank you. Press up. Let P now be in S2. This time we're going to show it being in S2 means it's in S1. Okay, so start out with P's in S2. If P's in S2, what do I instantly know about P?
On the perpendicular bisector.
It's on the perpendicular bisector. Well, first off, let's handle the case where it's on. If P, so let P in S2, and note if P's equal to O, then obviously P's in S1.
Yeah.
Because O is equidistant from A and B. So we handled the case where P's O. So now let's handle the case where P isn't O, it's some other point. Now it's on this perpendicular bisector. So one, I know that OP is, that line is a perpendicular bisector. So I know this distance is the same as this distance. Furthermore, I know these are right angles. Look at these triangles. What do we know?
They're
They're
going to be congruent.
congruent based on side angle side.
Side angle side. Wait a second. I only have two sides. I only have one side from each and one angle from each.
What?
Where am I going to get my other side? They're sharing a side. this side is congruent to, wait for it, this side.
Yeah.
So side, angle, side, side, angle, side. The two triangles are congruent. And so if the two triangles are congruent, how does AP compare with BP?
They're congruent. They're the same.
They're congruent. So that's going to give me that this side is congruent to this side. And so the distance from A to B is the same as the distance from B to P. That's exactly what it means to be in S1. Your distance from A and your distance from B are the same.
Yep.
So now just restating that in words. Let P be some point in S2. And note if P is equal to O, then P is in S1 and we're done. If P is not equal to O, then since AO is congruent to BO, and OP is congruent to OP, noting that those sides are congruent to each other, and this side is congruent to, those sides are congruent to each other, and this side is congruent to itself, then triangle AOP is congruent to triangle BOP by side angle side. And since they are congruent triangles, their hypotenuses are congruent to each other. AP is congruent to BP, the hypotenuse, which is exactly what it means to be in S1. So therefore, P is in S1. So I showed, let P in S2, therefore, P is in S1. If it's in S2, it's in S1. That's exactly what it means for S2 to be a subset of S1. So I have S1 is a subset of S2, and S2 is a subset of S1. That's exactly what it means for the two sets to equal each other. And therefore, that is the exact same set of points. So there is no difference between the set of points equidistant from A and B and the perpendicular bisector to the line segment AB. Those are identical geometric figures. And that's how you would prove it. Good?
Yep.
Any questions so far? Focusing more on the proof style than the actual substance. Alright, I'll do one more of these proofs where I write it out completely and then we'll be done writing them out completely. Okay, so our next one, Theorem 3.2. Here we're going to prove that the locus of points interior to an angle and equidistant from its sides are the angle's bisector, minus the vertex, because we're talking about the interior. So what do I mean? Start out with some angle AOB here. Draw the line in the interior of angle O, and the rule is the line as we draw it has to be equidistant from both the sides. Now over here, start out with angle AOB, and instead draw the line that bisects the angle, splits it so that this angle is congruent to this angle. So in one case, I know that this S1 is equidistant from both sides. In this case, I know that S2 divides it so that this angle is congruent to that angle. We're going to prove that those are the same segments. Now, before we can do this, we really need to define what it means, for what we mean by a point's distance from a line. We have to be a little bit careful as to what we mean by a point's distance from a line. If I've got some line here, and I've got the point P here, how do I get its distance to the line? I can't just arbitrarily take some measuring tape and measure. I can come, stick my tape right here, come over here, measure it, and I get 25 feet. Is that how far that point is from that line? No.
Point on the perpendicular bisector.
Not necessarily
Not bisector.
bisector, but what we mean by the distance from a line to a point P is construct the perpendicular to the line that goes through P, and now the length of this segment is its distance. So we always use the perpendicular when we talk about a distance. That make sense? Okay, so up here, remember what is S1? It's a set of all points whose distance from this line is equal to their distance from this line. What does that mean? That means when you pick a point P in S1, if I draw the perpendicular from this side, and I draw the perpendicular from this side, both the perpendiculars that intersect P, the length of that segment has to be equal to the length of that segment. So that's what we instantly know if you're a member of S1. If you're a member of S1, if P is in S1, its distance from this line and its distance from this line are the same, or in other words, AP is congruent to BP. That's what it means to be in S1. Right? And what it means to be in S2, if P is in S2, that's going to mean this angle, BOP, is congruent to this angle, AOP. That's what it's going to mean to be in S2. So just understanding what it even means to be a member of the set, and what we mean by the distance a point is from some line. Good so far? Okay, so with that, let's start jumping into the actual proof. So let S1 be the locus of points interior to angle O and equal distance from its sides. S1. Note, is O in S1?
No.
Isn't it equidistant from both the sides?
I don't think you made a distance there. It's part of the line.
Huh?
It's part of the line.
Yeah, so what's its distance from the line?
It doesn't make, that doesn't make sense.
A distance can be 0.
It's not.
You can talk about the distance from a point to itself. One of the definitions of a metric is the distance from a point to itself is 0.
Yeah, it is.
So is O part of this line? S1. What is S1? Let S1 be the locus of points interior to angle O.
It's not in the interior.
Oh, it's not in the interior. So S1 is the locus of points interior to angle O and equidistant from its sides. So no, it doesn't include the point O. And let S2 be the bisector, not including O. And that's why we said not including O on the bisector. Because we're trying to show that the set of points are the same, but we got to make sure we don't get O then. Because this one doesn't include O, so we took O out of this. We're saying with the exception of O, they're the same. Okay, just making sure you understand why we had that minus the vertex here. Okay, understand what we're trying to prove?
Yeah.
Alright. So then, let's get started. I gotta pick a point out of S1 and show it's in S2, and then pick a point out of S2 and show it's in S1. So let P be in S1. And let A and B be the bases of the lines perpendicular to angle O's sides going through P. What is A? It is the base of the perpendicular to this side going through P. And what is B? It is the base of the perpendicular to this side going through P. That's what A and B are. And note that AP is congruent to BP. How do I know that AP is congruent to BP?
Because.
That's what it means to be in S1. S1 means you're equidistant from both sides. This is a bisector that gives, or this is a segment that gives me the distance to this side. This is a segment that gives me the distance to this side. I know that P is equidistant from both sides. By definition, what does that mean? That means that this segment is congruent to that segment. Because those are the segments that give you the distance. That's what we mean by the distance from a point to a line. Take the perpendicular that goes through that point. The point at its base, A, to that point, that length is what we mean by that distance. So we know that AP is congruent to BP by definition of S1. With me so far? Okay. Now what are we trying to argue? I'm trying to argue that P also lies on the angle bisector. In other words, I'm trying to argue that this angle is congruent to this angle. Make sense? So here's the information we know. I'm trying to argue that this angle is congruent to this angle. Let's just look at the picture and reason through it for a second. Obviously, if I can show that the bottom triangle is congruent to the top triangle, we're done. Because then that angle is congruent to that angle. So I'm trying to argue that those two triangles are somehow congruent to each other. What to do, what to do?
Angle, side, angle.
Angle, side, angle. Do we have another angle? We know that's a right angle and that's a right angle.
Oh, and then they're sharing.
They're sharing a side. Okay. So I know that side's congruent to itself.
They're also.
But we don't have a side-side angle congruency theorem.
Okay.
We have a side angle side.
What about?
We have an angle side angle. We have a side side.
Do we know OA is congruent to OB?
Do I know that OA is congruent to OB? Do we? How would I make that argument?
Excuse me and good morning.
Good morning.
How are you today?
I am lovely.
Never mind, I don't even need to ask. I need to not even ask how you are. Are we here?
We're missing Megan.
Can I have a last name?
Collie.
Okay, thank you
Thank
very
you.
much. Hey, if you guys can read that, I am happy for you, because I think I want new glasses myself now. Have a good day.
You too. All right. So I know that this side is congruent to that side. I know that side is congruent to that side, and we have the angles.
Oh, they're also a right triangle.
They're a right triangle.
Which
What do we love about right triangles?
they have the Pythagorean theorem.
The Pythagorean theorem.
Oh, which
Let me
means-
give you two triangles to help you in your shows up on state testing kind of way, right? Really simple-minded thinking.
Okay.
We've got those two are right angles. We know the hypotenuse is the same for both of them, so let's say that that's a 5 and that's a 5, right? And I know that these sides are the same for both of them. That's a 3 and that's a 3. Can I argue that these sides are the same for the both of them?
Yeah.
Yeah, using the Pythagorean theorem. Let's call this a distance A. What is A equal to?
This.
You know that A squared plus 3 squared equals 5 squared, right?
So it's equal to the square root of 3.
So A squared is equal to 5 squared minus 3 squared.
So it's
So A is equal to the square root of that. Now, 25 minus 9 is 16, and so A is equal to 4. But the point is, A is equal to that, and A is equal to that over here as well, right? So this side, whatever this side is, it's the square root of this side squared minus this side squared.
Yep.
So now let's just be more generic. Pretend that this was little c and this was little a. Then this here is c squared minus a squared. Similarly, if this was c and this was a, then this is just a square root of c squared minus a squared. And so, if you call that distance a and you call that distance c, that distance will also be a, then this will be c squared minus a squared under the radical, and this will be c squared minus a squared under the radical.
yeah.
So, since they have the same length, they're congruent.
Which means the triangle over here on that side and side.
And so, we know that this is the same length as that by the Pythagorean theorem.
Or side to side.
Huh?
They're congruent by side to that side or side to side.
Right. But, so we knew the segment was congruent to the segment by Pythagorean theorem is what I meant. And now, these two triangles are congruent to each other. You can use side, angle, side, or you can use side, side, side. Doesn't matter which way you go. And since the two triangles are congruent to each other, then obviously this angle is congruent to this angle. And so P lies on the angle bisector. OP bisects angle AOB. It splits it perfectly in half. Make sense? So continuing with just writing it all out. Since angle AOP, or OAP is congruent to angle OBP, and since they're right angles, and since OP is congruent to OP, then OA is congruent to OB. And how do we make that argument? By the Pythagorean theorem. So then angle, or triangle AOP is congruent to triangle OAP is congruent to triangle OBP. By side, 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 or side, angle, side, whichever one you want to use. Which gives me that P is in S2. Because this angle is the same as that angle. Probably should have written that first. So that gives me that this angle is the same as this angle, and so P is in S2. What is S2? It's a set of all points on the angle bisector. It's a set of all points such that OP splits it so that this angle is congruent to that angle. So we get that S1 is a subset of S2. Now we gotta go the other way. Prove that S2 is a subset of S1. So this time let P be in S2, and let AB be given as above. Or in other words, A and B are the bases of the perpendiculars to the sides that go through the point P. They are the segments that we are going to use to determine the distance to sides. So in this case over here, what am I trying to prove?
AP is congruent to BP.
I'm trying to prove AP is congruent to BP. I'm picking P so that it bisects the angle. My job is to prove it's also equidistant from the sides. So AP, that length, is what we mean by its distance to that side, and BP, its length, is what we mean by its distance to the side. So if I can show AP is congruent to BP, then we're done.
And you're going to do this by showing that the angle APO is congruent to BPO, and then using the shared side to use angle side angle.
Perfect. So we have this angle is the same as that angle. We have that angle is the same as that angle. And so what he's noting is, therefore, this angle has to be the same as this angle. How do we know?
Because the triangle's congruent by inside. Or
If a triangle, two triangles have two angles in common, their third angle has to also be congruent to each other. Yeah.
Similarity theorem.
Well, you can view it as a similarity theorem, or you can view it, it just comes from the fact that the angle sum of any triangle is a straight angle, or 180 degrees.
Yeah.
If this is 90 degrees and that's 30 degrees, this has to be 60. So if that's also 90 and that's also 30, that also has to be 60.
Right. Yes.
So regardless, since all three of these have to sum up to the same thing as what all three of these sum up to, and since those two are the same as those two, then that one has to be the same as that one. Make sense? So that's the thinking he was using there. So I know that this angle is congruent to this angle. Now, still trying to prove that this triangle is congruent to this triangle. So now, Alex, how do we continue?
They also share a side.
They also share a side. This side is the same as that side.
So they're congruent by inside.
And so by angle, side, angle, angle, side, angle, the two triangles are congruent to each other. Which gives me that this segment is congruent to that segment. So writing that out in words, let P be an S2 and let A and B be as given above. So exactly how we have them shown in that picture. Since angle AOP is congruent to angle BOP, this is congruent to this, AOP congruent to BOP, and since angle APO, that right angle at the top, is congruent to angle BPO, the right angle, oh no. Oh yeah. Did I write that backwards? Or am I just keep looking at it wrong?
APO.
OPA. This is not supposed to be APO. This is supposed to be the right angle.
OAP.
OAP is a good way to do it. All right. Angle OAP is congruent to angle OBP. Okay, the right angles. This right angle OAP is congruent to this right angle OBP. Then the resulting angles OPA is congruent to angle OPB. So then that gives me that the two triangles are congruent by angle, side, angle, since they share a side. Probably should have specified that. Which gives me that AP is congruent to BP. So its distance from either side is the same. So P must also be an S1. So I showed that S2 is a subset of S1. We showed S1 is a subset of S2. We showed S2 is a subset of S1. Therefore, S1 equals S2. Good? All right. That's the last time I'm going to fully write out one of these proofs. Common proof style, though, to show that the sets are equal to each other. So start moving faster through these theorems now, and just rely mostly on the pictures. So next, let AB with midpoint O. So let's see what this one's saying. Here's A, here's B, and it has midpoint O. The set of all points P that make triangle APB right, with AB as a hypotenuse, are the circles centered at O with radius OA. Let me draw this picture a little bit bigger. Or we'll do two pictures. So there's one picture. We'll have a bottom picture here. Try and draw my circle first. Terrible circle. Although I'm not sure I'm going to get much better. Need a compass for my chalkboard here.
Do those exist?
Yes, they do. There used to be one in here, and I don't know what happened to it.
It's false, actually.
Very useful for a terrible artist like me. Okay. So here's A, here's B, here's O. So in the first case, what are we doing? I'm starting out with trying to make these look somewhat similar to each other. Trying to roughly the same length. So looking at the same exact segment two different ways. So in one case, Up here, I'm going to pick some point P, such that when I construct a triangle using that point P, it gives me a right triangle. Pick any point P such that the triangle results in a right triangle where AB is the hypotenuse. Down here, pick any point P on the circle. All these points are going to be the same as all these points. That make sense? Okay, so let's see which way we want to go first. The set of all points P that make triangle APB right, with AB as the hypotenuse, are the circle O with radius OA. So, let's start out with P here. And what do I know about P? P is a point such that triangle APB is a right triangle where AB is the hypotenuse, or in other words, APB is a right angle. That's what we know about it. What am I trying to prove? I'm trying to prove that P lies on the circle centered at A that goes through these points. I'm trying to prove it lies on this circle. Centered at O. So it has to go through A and B. That would make it centered at O. That's what I'm trying to prove. With me?
We already proved this. Let's look and prove this.
We proved that every right triangle can be inscribed in a semicircle. Or sorry.
Yeah.
We proved that any triangle inscribed in a semicircle is a right triangle. So the bottom direction we got for free. This one we have to do a teeny bit more thinking. You with me? Okay, so first off, I instantly know right out the door that every triangle can be inscribed in one and only one circle. So first, let's create the circle that inscribes a triangle. So here's a circle that inscribes a triangle. I do not, as of yet, know that that circle has O at the center. I need to argue that. Because what this picture could look like, bad picture, but just to give you a sense for what the picture could look like, forget it, not going to draw a good circle. Maybe my triangle looks like this, where this is a right angle. Maybe O here didn't perfectly lie at the center of the circle. Impossible picture, but I need to argue that that's an impossible picture. So I need to somehow argue that O here is the center of the circle, and we're done. So I constructed the circle. I know there's one and only one circle that goes through all three vertices. I'm already given that. Now I need to argue that my picture doesn't look like this, and that O is in fact at the center of the circle. You with me? Okay. What do I know about angle APB? It's a right angle. And it's, what is that angle relative to the circle?
It's a inscribed angle.
It's what we call an inscribed angle. Right?
Yes.
Now, if we pick some other point O prime, so here's O, let's say that O prime is what we call the actual center of the circle. O prime. What is angle AO prime B?
That's going to be straight angle. Because it has to be twice your.
Yeah, in this case, O and O prime are the same point, but how do you know it wasn't this? So here's A, here's B, drawing it as a bad picture. Let's look at angle AO prime B. How big is it, this angle?
Should be straight angle.
How do we know it has to be a straight angle? Here's the right picture, here's an impossible picture. So how big is AO prime B? AO prime B, how big is that angle?
Twice the size of
Your inscribed
the
angle.
It has to be twice the size of your inscribed angle, going back to this theorem. If your inscribed angle is psi theta, your central angle is 2 theta. If your inscribed angle is 90 degrees, your central angle has to be 180 degrees. Which means that O prime is between A and B. The center of the circle is between A and B. And it has to be in the middle between A and B, because A and B have to be the same distance from that point. So O prime is O.
Wait, how do we know O prime has to be the same distance from A and B?
Because A and B lie on the circle. What does it mean to be on the circle? It means your distance from the center is the same.
Gotcha.
Good? So, remind you of the steps we went through. First, construct the circle centered at O prime that goes through A, B, and P.
Yep.
Since angle APB was a 90-degree angle, angle AO prime B had to be a straight angle. So O prime had to lie between A and B. And so O prime was in fact O. Because we already chose O to be the midpoint between A and B.
So why don't we need to inscribe a triangle and circle?
What are we trying to prove? We're trying to prove that P lies on the circle centered at O with radius AB. That's what we were trying to prove. So we picked the circle that A, B, and P for sure lie on, which is one and only one circle, and we need to argue that that circle was centered at O, and then we were done. So P, in fact, lies on the circle centered at O.
Okay.
Or, strictly speaking, it lies on the circle centered at O with radius OA. I'm not specifying the radius. Good? Okay. Now the other direction. The other direction, we start out with a circle that has AB as its diameter. Pick any other point on that circle. We need to argue that the resulting thing is a right triangle.
Did we prove that already?
We already proved that. And we proved that before we had this theorem, and so we proved that the hard way.
Right.
Now we can prove that the easy way. This angle is a central angle. This is an inscribed angle. It has to be half that.
That's right. Sweet.
So you can just use that theorem again to argue for it if you want. If you don't remember that we already proved this. Pretty simple. Good? Okay. And again, if you were writing this all the way out, you would do it the way we did this. Let P be a point in S1, da da da, therefore it's in S2. So the style of proof would be this. I'm just done writing out the style. Because it's kind of tedious writing it out. Yep. Okay. Now we get to prove 4 absolutely amazing properties of triangles. Which is, intuitively, it's like no matter how we decide to draw lines through these things, as long as we're doing it in some common way for all the lines, they always keep intersecting at the same point. What do we mean? So in our first one, what we're going to prove is draw the angle bisector for B. That's what this purple line is. Draw the angle bisector for C. That's what that purple line is. Draw the angle bisector for A. That's what that purple line is. And they all intersect at the exact same point. All 3 of them go through the same point. Then we're going to say, okay, let's come at it a different way. This time, let's draw the perpendicular bisector of this. So cut this perfectly in half, draw the perpendicular line. Do that for this side, and this side. Those all intersect at the same point. Okay, let's try something else. I'm going to take the midpoint of one side and connect it with the vertice. Take the midpoint of this side, connect it with the vertice. Take the midpoint of this side, connect it with the vertice. And all those 3 lines, I didn't draw this one because it will interfere with our proof, but all 3 of those go through the same point. And I'm like, okay, that's crazy. What's the last one? I'll draw it over here because you'll get confused by that picture. Pick any triangle you want. Draw the altitudes. The altitude means drop a line down from this vertice. So that creates a right angle with this side. Drop one down from this vertice, so it creates a right angle with this side. Hard to kind of just do it on the fly. And then do it with this one. And all 3 of those will intersect at the same point. So 3 different ways of cutting up triangles, and they keep intersecting at the exact same point every time. That's what we are going to prove. So for the first one, now exactly what we're proving. The angle bisectors of a triangle. So what are the angle bisectors? They're the lines that split each angle in 2. So every triangle has 3 angle bisectors. The angle bisector for this side is this purple line. It should go on all the way, but I'm just stop drawing it when we get to the point. The angle bisector for this side is this purple line. The angle bisector for this side is this purple line. The angle bisectors of a triangle intersect at a single point. We call that point the incenter. And that point is equidistant from its sides. So the distance from where they all intersect to this side is the same as the distance to this side is the same as the distance to this side. So I'm going to be arguing 2 things, that all these intersect at the same point, and that all those red segments are the same distance. Go ahead.
Is Incenter official notation of
Yes, we've already talked about the incenter before. The incenter is the center of the circle that is inscribed in the shape. So if I were to draw the circle that's inscribed in the shape, the circle that's tangent to all these sides, it would be centered at that point O. And in fact, these would be the points where that circle would be tangent to each of these sides. And so it would be the circle centered at O that goes through these. That would be its radius. Okay? So, arguing two things. I need to argue all the angle bisectors go through the exact same point, and that distance is the same as that distance is the same as that distance. The distance from the point to that side is the same as the distance from the point to that side is the same as the distance from the point to that side. What do we mean by the distance from a point to a side? Draw the perpendicular to that side that goes through that point. So these are all the perpendiculars that we're going to be interested in. Make sense? Okay, so let's start the proof. So start out with, I know all the angle bisectors, so I know everything in purple. I know that's an angle bisector, so I know that those two are congruent to each other. I know that that's an angle bisector, so I know that those two are congruent to each other. Let's kind of forget this top bisector for a second. And so we're just looking at this line and this line. With me? Now, how does this triangle compare with this triangle?
Oh, yeah.
How do I know that this triangle is congruent to that triangle?
13.2. Theorem 13.2.
It's side angle side, angle side. Or angle side, angle side.
He's seeing it, I think, not 13.2.
Angle side.
Oh yeah, 13.2. We just have the picture up there.
Yeah.
What did Theorem 13.2 say? It said that the angle bisector is also equidistant from either side. Since I know that purple here is an angle bisector, I know that this distance is the same as this distance. And since I know that this is an angle bisector, I know that this distance is the same as this distance. With me? So, I know that this triangle is congruent to this triangle, and this triangle is congruent to this triangle. You with me? So, wherever this angle bisector and this angle bisector intersect, it's for sure equidistant from all three sides. Right? And now, how do I know that this angle bisector also goes through that exact same point? So I know that these two angle bisectors obviously intersect at one point, because they're non-parallel lines, so they intersect at a point, one point. How do I know that this one also goes through that exact same point?
Also by 13.2 because of the two line bisectors. Perpendicular bisectors.
Yes. Also by 13.2. Since it's equidistant from both sides, that point is, it has to be on the angle bisector. So, follow the logic here. We start by drawing these two. Ignore the top purple for a second. We draw those two. Since those two intersect at that point, from 13.2, I know that those two are congruent and those two are congruent. Now, O is equidistant from this side, and O is equidistant from this side. So it has to lie on this one's angle bisector using 13.2 again. Follow the logic there?
Yeah.
That's all there is to it. So, those three bisectors intersect at a single point, and that single point is equidistant from all three sides. We call it the incenter because it would be the center of the circle inscribed in the triangle. And that circle would have this as its radius. And so those 3 points would be the only points on the triangle, also on the circle. That's where it would be tangent to each of those. See it? Okay, next one. The perpendicular bisectors of a triangle's sides intersect at a single point, equidistant from the vertices. And we call this one the circumcenter because it's the center of the circle that circumscribes a triangle. If I drew the circle that went through all the points A, B, and C, it would be centered at O. And so the distance from O to A would be the same as the distance from O to B would be the same as the distance from O to C. Because A, B, and C lie on circle O. So once again, starting out with the purple. So we got our triangle ABC here. And now I draw all the perpendicular bisectors. Perpendicular bisector, 1, means it bisects it. So this side is congruent to that side. And it's a right angle. Perpendicular bisector, and it's a right angle. Perpendicular bisector, and it's a right angle. I need to argue two things. I need to argue that all the red lines now are the same length, and that wherever these two intersect, this one also intersects at that point O.
How do we know that the perpendicular bisectors all intersect at one point?
Well, we know two of them for sure intersect at one point.
Yeah.
So this one, maybe it does, maybe it doesn't. We'll say, we're not sure. Is that going to go perfectly through it, or is it going to miss? So we'll start with that.
Okay.
With me?
Yeah.
Okay. So, here's where we are so far.
Yep.
I'm trying to argue red are all congruent to each other.
You can use side angle side to.
Side, angle, side, side, angle, side to say these two triangles are congruent to each other.
Yep.
So I know that red, now it's 4, I know that that is congruent to that.
Yep.
And the same if you look at these two triangles, it's the exact same type of thinking. So I know that that is also congruent.
So there we go.
Okay, so we got to there. So now I need to argue that O lies on the perpendicular bisector of this sink.
Use 13.1. So we know that O is equidistant from AC and BC. So it's on the perpendicular bisector of AB.
Perfect. O, its distance from A is the same as its distance from B.
Gotcha.
And so it lies on the perpendicular bisector.
Yeah.
And so all three of those points intersect at a single point. And that, in fact, does go through it. Good? Cool. Next one. Okay. The medians. What is the median of a triangle? Let me just scribble it to the side really quick. So if I have some random triangle, the median is take the midpoint of this side and connect it to the opposite vertice. Take the midpoint of this side, connect it to the opposite vertice. Take the midpoint of this side, connect it to the opposite vertice. Those are the medians. We're going to prove that all the medians go through the exact same point.
That's good. Okay.
Now we're going to prove it so that I'm going to start out with just two medians. And then the proof can be done again for the third. You'll see what I mean.
Okay.
So starting out here, we're going to prove that the medians of a triangle intersect at a single point. This one's called the centroid. So different from the incenter or the circumcenter, it's called the centroid, which is located exactly 2/3 of the distance down each median. So in other words, wherever they intersect, if this distance right here is little a, then this distance right here from here is 2 little a. And if this distance is little b, then the distance from here to here is 2 little b. And if this distance is little c, then the distance from here to here is 2 little c. It always cuts them all in 2/3 ratios, 1 to 2 ratios.
Is this how we get our formulas for the bottom of it?
You could use this if you wanted.
Because I remember that came up a lot when I was doing that.
Yeah, but I gave you 30, 60, 90 triangles, or 45, 45, 90, so that you could just do the algebra.
Yeah.
So you didn't have to rely on this proof, but you could have used this fact.
That makes a lot more sense now.
Yeah, and you notice that in that special case, it cut it exactly at a ratio of 1 to 2. And that wasn't an accident. And not only does it work in those triangles, but it works in all triangles. Okay. So, start out with two medians here. The median BE and the median AD. Now, since AD is a median, that means D is the midpoint of this side. And since EB is a median, E is the midpoint of this side. So in other words, I know that this is congruent to that, and I know that this is congruent to that. With me? What am I trying to argue? First off, I know that the two medians intersect at one point. Okay, that's trivial. So first thing I need to argue is that point lies at a 1 to 2 ratio. That this distance is double that distance, and this distance is double that distance. You with me?
Yeah.
That's what I'm going to try to argue first. And then we'll introduce the third line and argue how it also goes through the same point.
Okay.
It's very similar to how we did these ones. First, I showed that the sides are all equal, then that all the points are at the same point. All the sides are equal, then all the points are the same point. So, all the sides are a 1 to 2 ratio, then all the points are the same point. Okay. So now, consider this line ED here drawn in purple. What do I know about ED?
It's parallel to AB.
It's parallel to AB. How do I know that?
Because it goes through both of the other sides.
Because it cuts these at the same ratio. That's going all the way back.
The 9-1.
Way, way back, whenever we did similar triangles. Chapter 9 sounds about right.
That should be theorem.
I think it was a corollary to that theorem.
Yeah.
So if it cuts a triangle so that this segment is congruent to that segment, then it also cuts it so that this segment is congruent to that segment, if and only if it's parallel
Wait, yeah, okay.
to the base.
Right.
So I know that this purple is parallel to this line down here. What does that give me?
You can use your corresponding angles probably.
Corresponding angles. So that gives me that this angle, here's a transversal going through two parallel lines. And so its corresponding angle
UDA.
is congruent, right? Similarly, if you think about this as a transversal, this angle is the same big as
That angle.
that angle. Cool? You can see what we're building up here.
The angles in the middle are congruent by vertical angles.
And that is congruent to that since they're vertical angles. If we want to use that fact. Probably useful to see. So now what?
Well, the two triangles are similar.
This triangle is similar to that triangle.
Yeah.
Yeah.
What do we know about similar triangles?
They all have
The sides are
similar
proportional.
angles.
The sides are proportional.
Yeah, they have the same angles, but more importantly, their sides are proportional. What am I trying to argue? I'm trying to argue that the proportionality of this to this is 1 to 2, and that the proportionality of this to this is 1 to 2, and that the proportionality of this to this is 1 to 2. If I can get one of those proportionalities now, I get the other two for free, because that's what needs to be similar. So I know that this triangle is similar to this triangle. How am I going to get my 1 to 2 ratio going?
I want to say your parallel lines. Because
Yeah, your parallel lines.
there's a theorem about it.
This to this is a ratio of 1 to 2. How do I know that?
I'm trying to remember.
So here's how we can get that. Do this in red. This angle is the same as this angle. And this angle is the same as this angle. And the top is the same for both of them. Right?
Yeah.
So this top triangle is similar to the bottom triangle,
Yep.
which means that the ratio of this to this
Oh, that's right.
is the same as the ratio of this to this is the same as the ratio of this to this.
Which is 1. Okay. Yep.
So if I call this distance up here little a, what is this distance then?
2A.
2a.
Sweet. So now we have that for all of ours.
And so now I know that the ratio of this side to this side is 1 to 2. And since this triangle is similar to this triangle, that same ratio holds. So if this right here is little b, then this side has to be 2b. And if this side right here is little c, then this side has to be 2c. You see it?
Yep.
So that point lies exactly 2/3 of the way down each median.
2/3.
Yeah. 2 out of 3.
Oh, okay. Gotcha.
You can also think about it as 1/3 if you think about it as counting from the other way. It's typical to think about the median as coming from the vertice, but it's completely arbitrary. It cuts out a ratio of 1 to 2.
Yeah.
Okay.
Sweet.
So now, what do I need to argue? I need to argue now that the median from C also
Goes to that point.
goes through that exact same point. That's what remains to be shown in this proof. Now, I know that the median from C and the median from B intersect at one and only one point.
Yes.
And using the exact same logic, it has to occur at a point 2/3 down from B's vertice, which is that point. So where this one and this one intersect, you just like redo the exact same proof, and they intersect at the point that cuts this at a ratio of B to 2B. There's only one place where that happens.
There's that one. Okay.
And it's that point. Does that make sense? So that's why I left the top off. You see that the picture gets messy here, but so it's just repeating the proof, flip that way. And just make sure that we still call that B, and it's still going to be B to 2B.
Okay.
That's a single point. So it goes through that exact same point. That all makes sense? Okay. Now our last proof that we're doing is the one for the altitudes. Ignore purple for a second. Start with triangle ABC. This is our starting triangle. I drew it upside down. I drew it upside down because I think it's easier to see the proof that way. Okay, so here's triangle ABC. And we are proving that all its altitudes intersect at a single point. The altitude is draw a perpendicular to AC that goes through B, draw a perpendicular to BC that goes through A, and draw a perpendicular to AB that goes through C.
Yep.
We're trying to prove that all those altitudes intersect at a single point. With me so far?
Isn't that obvious?
No.
Oh, okay.
Okay, so how do we do this proof? This proof, we're kind of like inscribing this inside of a triangle. What I do is I construct through A a line parallel to BC. So I constructed this purple line so that it's parallel to this line. And I construct this purple line, EF, so it's parallel to this line. And I construct this parallel line so it's parallel to this line. You with me? And then just label the points where all the parallel lines intersect as D, F, and E. With me so far?
Yep.
So notice that that creates this bigger triangle. Now, how does this bigger triangle compare with all these other triangles? Let's start labeling some stuff really quick. If this is that angle, then notice that that's also going to be what this angle is, because these two lines are parallel.
Yep.
That's corresponding angles. Over here we use alternate interior angles. Sorry, I think I said corresponding.
What do you say corresponding for all?
Okay, this was alternate interior is what we kept using.
Yeah.
Over here, this is actual corresponding angles. Okay, sorry, keep my terminology straight. And then, I also know that this angle, whatever that angle is what this angle is. Right?
Mm-hmm.
Now, because these two lines are parallel, whatever this angle is what this angle is. And since these lines are parallel, then whatever this angle is what that one is. And then the remainder on this one has to be the same as the remainder on this one. Once they have two angles in common, they have all three, right? Has to be the same as the remainder on this one.
So all triangles.
Now, I know that 1 and 2 and 3 give me a triangle. Over here, give me a straight angle, right?
Yeah.
I'm calling it, if it has one line, I'm calling it 1. If it has two lines, I'm calling it 2. If it has three lines, I'm calling it 3. So 1 plus 2 plus 3 is 180. Check that algebra.
Yep.
Right?
Yeah.
And so over here we have a 2 and a 3, so our missing angle must be a 1. So whatever this is just a 1. And over here we have a 1 and a 3, so its missing angle must be a 2. And similarly, this one is missing a 3. And so you see that this interior triangle is similar to all these other triangles, right?
And similar.
But notice that not only are they similar, but they all share sides. And so by side, angle, side, all these triangles are congruent to each other. You see it?
Yep.
Okay, since all these triangles are congruent to each other, the important part is the side between 2 and 3 is the same big as the side between 2 and 3. The side between 1 and 3 is the same big as the side between 1 and 3. The side between 1 and 2 is the same big as the side between 1 and 2. Right? And I won't bother labeling the interior anymore. But now notice, the red line here is the perpendicular bisector of big triangle. The altitude of the small triangle is also a perpendicular bisector of the big triangle, if I kept drawing it. Because it starts right at the midpoint and it's perpendicular.
Yep.
It starts right at the midpoint and it's perpendicular. It starts right at the midpoint and it's perpendicular.
Does that imply that it goes through E, or is that just how the picture's drawn? Okay.
We know that all the perpendicular bisectors of the triangle intersect at one point. So since all the altitudes of black triangle are perpendicular bisectors of purple triangle, they all intersect at one point. And we call that point the orthocenter.
Oh, cool.
Yeah, so the only trick to this problem was encase it in a triangle where the altitudes turn into perpendicular bisectors, and we piggyback off of our first proof there.
Neat.
That make sense?
Yeah. Cool.
There we go. That's all there is to it.
Is that all on chapter 13?
That's all chapter 13. These chapters are going to get much, much easier. The homework's going to get much, much easier.
Sweet.
I know that looks like we did a lot, but if you watch what the author does in the book, I give a lot more explanation than he bothers giving.
Does he prove these theorems?
Hardly. I think 2 of them were left as exercises to you guys.
Okay. Sweet.
But I hate when he does that. Huh?
He does that a lot.
He does do that a lot, and I don't like it, which is why I usually just prove all the theorems.
Oh, I appreciate that.
Okay, any other questions you want recorded? All right.